Thank you very much. I feel apologetic about a couple of things. One is that we're going to now transition from slides in English and a few English words to an entire presentation. But if I tried to do this in Italian, we'd be here all day. So I won't. I am also going to talk about a much narrower subject, which is not food itself. Probably you expected someone from IARC to talk about the recent evaluation of red meat. But as Roberta explained, I was asked to speak about pesticides, and I hope to convince you that these really are relevant to the themes we've just heard about, even though I won't say anything about trade agreements or globalization or meat. I think that what you will see does have direct relevance to the theme of this session. So let me start. The information that I'll present really comes from the IARC Monographs program, so I want to say a little bit about how this works. Many of you, of course, know the IARC Monographs. One of the grand figures in Italian epidemiology, Lorenzo Tomatis, is often considered to be the founder of the IARC Monographs program back in the 1970s. This program was actually initiated at the request of governments who wanted to know what the carcinogens were. Give us a list. Well, there wasn't such a list, and so the program was launched to evaluate primarily occupational and environmental exposures in the beginning, but since it has expanded into other realms, including foods, as you know, almost 1,000 agents have been evaluated since the beginning of the program. These evaluations are used, of course, not only by researchers, but by governments worldwide to take action and to set policies about health and to regulate carcinogenic exposures. One of the things that makes the monographs unique is that all of the processes that go into evaluations for the monographs are guided by a transparent, publicly available document known as the preamble. You see it here. This little book. Somehow I can probably point to things like that. And importantly, although many other agencies worldwide do evaluations of potential carcinogens, the monographs are unique in the sense that they do have this public guiding document that lays out procedures for evaluation free of conflict of interest with standardized criteria for evaluating evidence and reaching an overall evaluation. The monographs bring together three streams of evidence: data about cancer in humans, cancer in animals, and mechanistic data. And we'll focus on the human data because this is a group of epidemiologists, so this is most interesting for us. It's helpful for you to know the classifications and what they mean. Sufficient evidence means a causal relationship has been established such that chance bias and confounding can be excluded. A lower level of evidence would be what's called limited evidence, meaning that a causal relationship is credible, it's believable, but still chance bias and confounding could not be excluded. And then the next level down is inadequate evidence, which means that the available studies don't permit a conclusion as to carcinogenicity. Now, this could be because there are no human data, or it could be because there aren't enough studies, or it could be because the studies are contradictory and don't give any clear result. There actually is a fourth category, evidence suggesting lack of carcinogenicity, but it's not relevant for us today, so I won't say anything about it. It's also helpful to know the overall evaluation scheme for bringing together the human and animal data. Sufficient data in humans automatically puts an agent in group 1, which means carcinogenic to humans. Limited data in humans could put an agent in group 2A, probably carcinogenic, or group 2B, possibly carcinogenic, depending on the level of evidence in animals. Inadequate evidence in humans could put an agent in group 2B or in group 3, which means not classifiable, again depending on the level of evidence in animals. Now, some other factors can come into play in the overall evaluation, and one of the ones that's particularly important is the mechanistic data. When the human data are less than sufficient, it's possible, for example, to have a mechanistic upgrade to a higher category based on strong mechanistic evidence in exposed humans. It's also possible, interestingly, to have a mechanistic downgrade if there is strong mechanistic evidence that a mechanism observed in animals doesn't apply to humans. And this becomes relevant for some of the pesticides. So now let's look at pesticides. Since the initiation of the monographs in the 1970s through 2014, 75 pesticides had been evaluated. In group 1 were the arsenical pesticides evaluated as part of the larger group of arsenic and arsenic-containing compounds. In group 2A, there was occupational exposure in spraying non-arsenical pesticides, so not really a pesticide in itself, but an occupational activity. And then 3 others upgraded from group 2B on the mechanistic evidence. 2B had 21, group 3 had 49, including some downgraded from 2B. And so what this tells you is that up until 2014, of all the pesticides evaluated, the human data were inadequate for the majority. There are several good reasons why the data could be inadequate. One is small numbers, because the prevalence of people with high exposure to pesticides is relatively low, and because some of the outcomes of interest are fairly rare. Also, for the purposes of the monographs, we really want data on specific pesticides, not pesticides in general or classes of pesticides, but particular ones. And it helps a lot if those data are quantitative. Those data are useful for establishing causality, including the existence of an exposure-response relationship. But many studies have not provided those data, at least in the evaluations done before this year. Exposure to multiple agents is also an interesting problem. People who use pesticides tend to use a lot of them, and the pesticides used change over time. So exposure to multiple pesticides is a challenge both for exposure assessment and for the analysis and interpretation of data. And finally, there's interesting potential for nonlinear effects because some pesticides appear to be non-genotoxic, bringing in a variety of other mechanisms like endocrine disruption and oxidative stress, which may not operate in a linear way. So there are a number of ways that we could proceed to identify new pesticides for evaluation or for reevaluation. One would be to ask experts. And in fact, IARC convenes expert advisory groups about every 5 years to advise on agents to be evaluated in the coming years. This was last done in 2014. One of the results of that advisory meeting was a recommendation, in fact, to look at red meat and processed meat. Another one was that a number of pesticides were given high or medium priority for new evaluations. And this was based largely on suspicion of carcinogenicity, of course, but also evidence of widespread use and new data. I'll just point out some of the interesting pesticides here. In the medium category, you see DDT, which is sort of the iconic pesticide of all, you know, the one that really started the environmental movement back in the 60s. And of course, it was one of the very first globalized, well, it was the first globalized pesticide, I would say, which was heavily used in agriculture for many years, as well as in public health. I also see malathion, diazinon, and lindane, high priority agents, some of them actively used today, and glyphosate here, which is the active ingredient in the herbicide Roundup, which is tightly integrated with the system of cultivation of many genetically modified crops used largely for animal food, in fact. Another way we could approach this would be through a novel tool that we use based on chemoinformatic data mining. I won't explain how all this works, but essentially it is a computer-driven process for surveying all of the available scientific literature and analyzing the availability of information about chemicals. So applying this to pesticides produces these very nice diagrams like this. These beautiful star charts show you, focusing on the top on organophosphate pesticides and later at the bottom on organochlorine pesticides, first clusters of related compounds, and the amount of literature available on individual ones, with the size of those nodes showing the total amount of literature and the color, with red being the hottest, showing the amount of epidemiologic literature available for these. So from this exercise and the advice of the advisory group, we chose 8 pesticides for evaluation in 2015. You see them here. I've mentioned some already. Also tetrachlorvinphos and the herbicide 2,4-D, which is also heavily used in agriculture and is likely to see expanded use in the coming years. So some of these are interesting because they've been evaluated by other agencies more recently than by IARC. For example, the US EPA has considered some of them to be suggestive evidence of carcinogenicity. Some have been evaluated by the US report on carcinogens. And some of these are very high-use chemicals. So now we'll get into the evaluations, and I'll start with the simplest ones and build up to more interesting and complicated ones. So this is lindane, an insecticide that used to be more widely used than it is now. It's now highly restricted, but still interesting. For this one, most of the data are available for non-Hodgkin's lymphoma. There was a relative risk over 2 in the US Agricultural Health Study, a large prospective cohort study that did a careful assessment of pesticide exposures. This study also found a significant trend with increasing use. Another interesting study was a cohort of Icelandic sheep farmers, which showed increasing risk of NHL with the number of sheep treated with lindane to eradicate parasites. There were also positive associations in case control studies in the US and Canada. And interestingly, studies that used biomarkers for lindane exposure provided inconsistent results. But nevertheless, looking at this, with consistent results for lindane itself, in only a small number of studies, but no negative results, the working group concluded that this was sufficient evidence of carcinogenicity in humans. Sufficient evidence in humans automatically means group 1, but there was also sufficient evidence in animals. Now, a somewhat more complex case is the herbicide glyphosate. For this one, again, not very many epidemiologic studies. There were positive associations in case control studies in the US, Canada, and Sweden that persisted after adjustment for multiple pesticides. But the agricultural health study in the US, in this case, didn't find an association, although the 95% confidence intervals included the point estimates from other studies. So the working group concluded that this was limited evidence of carcinogenicity. However, there was sufficient evidence in animals from feeding studies in rats and mice, which showed increased incidence of some rare tumors. And there was strong evidence of genotoxicity and oxidative stress from experimental studies. So putting all this together, we have limited evidence in humans, sufficient evidence in animals. This is a classic group 2A situation, but it's interesting to note that with the strong mechanistic evidence, it could have gone to 2A even if the human or animal evidence had been weaker. Now we'll move on to DDT. DDT has a much larger and richer database, and several interesting cancers were reviewed. Liver cancer is one of them. There were positive associations with cancer of the liver in 3 studies in China with rather high relative risks. The exposures to DDT were fairly high in this area, but there was no association with DDT exposures in a cohort study of Italian malaria control workers in Sardinia. Testicular cancer was also interesting because of its potential link with endocrine disrupting effects of DDT, which are suspected. Here there were positive associations with DDT measured in blood in 2 cohort studies, as well as in 2 smaller case control studies. No association in another case control studies, and opposite findings in 2 studies that looked at maternal exposure to DDT and the development of testicular cancer in young men. More data were available for non-Hodgkin's lymphoma. Here, the U.S. Agricultural Health Study again found a positive association with dose response for NHL. This was null in the Sardinian DDT sprayers. And other associations using measurements of DDT or its metabolites were inconsistent, as were data from case control studies using self-reports or expert assessment. There's been a lot of interest in the potential association of breast cancer and DDT, again because of the potential endocrine disrupting effects of DDT, but there, although many studies were reviewed, no clear association was found. This graph shows the evolution of the literature over the decade of the 1990s. Things really haven't changed very much since then, although there are more studies. What you see is that the initial studies found strong associations, but as more studies were done, the results really converged on the null, leading to a meta-odds ratio of about 1. And so the conclusions for the human data were that there's limited evidence for cancers of the liver and testes, as well as for NHL, but inadequate evidence for breast cancer. So turning to the other evidence, in animals, there was sufficient evidence for carcinogenicity, again from feeding studies in rats and mice, using DDT and its metabolites, with increased liver tumors and lymphomas in mice, interestingly, because those are the same tumors observed in humans in this case, and increased liver tumors in rats. Strong mechanistic evidence for immunosuppression, oxidative stress, and receptor-mediated effects, which seem to confirm that the endocrine disrupting activity of DDT. So again, putting this all together, limited evidence in humans, sufficient evidence in animals, leads to group 2A. And now the most complex case, really, not such a large literature, but interesting, and one that has changed historically. There are occupational cohort studies of a variety of different workers, pesticide manufacturing workers, pesticide spraying workers, farm workers, forestry workers, and even military personnel exposed during the Vietnam War, as well as population-based case control studies that have looked at 2,4-D. But a number of these studies were judged to be uninformative, either because they looked at mixed herbicide exposures to the entire class of chlorophenoxy herbicides, of which 2,4-D is one, or because of the possible contamination with dioxin, which pertains mostly to 2,4,5-T, a related chlorophenoxy herbicide. So many of the available studies that were included in the previous IARC evaluation of phenoxy herbicides were excluded as uninformative about 2,4-D specifically. The most data were available for non-Hodgkin's lymphoma again. Here, an increased risk was seen in a cohort of California farm workers. No overall risks in 2 cohorts of manufacturing workers producing 2,4-D, although in the most exposed group in an American cohort, there was an elevated risk over 2. Case control studies gave mixed results, positive in 4 studies, with dose response in 2 of those, but an equal number showed no association. The working group for this evaluation updated an earlier meta-analysis and systematic review on 2,4-D, which essentially showed null result. But an interesting thing was that the results seem to be very sensitive to the inclusion of studies that were adjusted for multiple pesticides. And these two forest plots attempt to show this. The top one shows the data adjusted for multiple pesticides exposure, and I think you can see that a number of the studies, sorry, these buttons are very close together, lie close to the null, giving a meta-odds ratio of about, meta-relative risk of about 1. But if you substitute less adjusted estimates, that is, estimates that didn't adjust for all the pesticides, then the meta-relative risk is a bit larger. So there was also some data on soft tissue sarcoma, which had been of interest in earlier studies, and a number of other cancer sites, but there were only a few studies and the results were inconclusive. So the working group concluded this was inadequate evidence of carcinogenicity. In animals, limited evidence from studies of injection and feeding in rats and mice, and there was strong mechanistic evidence for oxidative stress. So turning to the overall evaluation, with inadequate evidence in humans and limited evidence in animals, normally we would be in group 3, but here the evaluation procedures allow the working group some latitude in taking into account all of the evidence, including the mechanistic evidence and the views of a large minority of the working group, that the human evidence were at least at the upper limit of inadequate because of the indications of stronger risks of non-Hodgkin's lymphoma among the most exposed workers in occupational studies. The working group decided to assign a classification of 2B rather than group 3. So some other pesticides that I haven't mentioned were also evaluated in the same meeting. You can see here that I didn't talk about malathion, but it was moved up from group 3 previously to group 2A. I didn't talk about diazinon, which had never been evaluated before, but it moved up to group 2A. Tetraglorfinphos also moved up from group 3 to group 2B. So these evaluations in the past year added one new group 1 agent, lindane, 4 new group 2A agents, of which 2 were classified for the first time and 2 were upgraded from earlier evaluations, and 3 new group 2B agents, which were either upgraded or classified separately for the first time. In conclusion, I think we can see that the epidemiologic literature on pesticides has evolved considerably over the years, but as we always like to say, further research is needed. One interesting thing that comes from these evaluations is that the biomarker studies that measured pesticides or pesticide metabolites in blood or adipose tissues gave really mixed results, and in many cases it was the studies that used more traditional methods that appeared to give more definitive answers. So improving exposure assessment in pesticide studies remains a very important task, as does understanding how to deal with multiple exposures, which has represented an important challenge throughout these efforts to study pesticides over the years. So that brings the presentation to a conclusion, and I thank you very much for your attention.